15.4 and 15.5 with you guys. 15.4 is actually pretty straightforward. You probably could do this by yourself without any explanation, but I will explain it nonetheless. So basically this section is about net force. And really up until this point what we've looked at, if you recall 15.3, hopefully you've watched that one. In 15.3 what we decided is that if two forces are acting in different directions and they're balanced by a third force, we can add them using the parallelogram method. So the question then becomes, well, what about unbalanced forces? Can we add them the same way? Of course we can. The answer is yes. So it's not just forces that are balanced that we can apply the parallelogram method to. The parallelogram method works with any forces acting in a plane, whether they are balanced or not. When we get down here to the word net force in italics, it doesn't really do a good job of giving you the definition. So let me give you my definition of net force. Net force is basically the combination of all forces acting on an object. Okay, so what we've learned so far is that when the net force is 0, that means the forces are balanced. If the net force is anything other than 0 and anything else, that means they are unbalanced. Okay, so now the rest of this section basically just goes on to show you how we can apply the parallelogram method to forces that are unbalanced. And you can kind of read through this. It explains it. So I'm just going to give you my verbiage instead of reading it right from the book. My spiel. So they give you this example in figure 15.8. So we start here and we go, okay, so if I have an object right here and it's this object is being acted on by three forces, one going direction A, one going in direction B, one going in direction C. If I knew the proportionality constant associated with these vectors, I could measure the length of the vector and figure out exactly how much force was going in each direction. Now, if I want to figure out what the combination is, the net force, I want to know the combination of all three forces. So if these three forces are acting on an object, where is the object going to go and with how much force? That's what net force is. So what is the result of those three forces acting on an object? So what they go on to show you, let's look at part B, is you can apply the same parallelogram method. But in this case, because we have three forces that we're looking at, we're going to start with any two and forget the third one for a second. So let's look at B and C for now. Okay, so if we have these two forces, pretend A doesn't exist, we can do our parallelogram method. So again, vector B and C would be 1/2 of the parallelogram. And then we're going to draw opposite lines that are equal in length and exactly parallel. So opposite lines are exactly equal in length and parallel. The result of our parallelogram, if we go over to the new corner that was just created and draw a line straight back to the origin, this is the direction of the combination of forces B and C. And again, if we knew the proportionality constant, we could measure the force, we could measure the vector, and figure out exactly how much force that would be. So if just B and C, if these were the only two forces acting on an object, the result would be some force in this direction. And again, we could quantify the force if we knew the proportionality constant. So D is the net force of B and C. It's the combination of B and C. Now, basically what we've done is we have accounted for both B and C already. So it's almost kind of like we can say now they don't exist. Now we just have A and D. Right? Because as soon as we account for B and C by combining them to create D, now B and C we don't really need to worry about them so much because we've already accounted for them. So now what we're going to do is basically we're just going to kind of pretend like now all we've got are vectors A and D. So now we just have to worry about those two lines, A and D, that's it. So what's the combination of those two forces? And that's what they show you down here. So again, just pretend if you can that B and C don't exist because again we've already accounted for them in force D. So we're going to take vector D and vector A and create another parallelogram to figure out the combination of A and D. So again, what makes this difficult to look at is that we can see these two, and there's all these lines and it looks confusing. So in your mind, envision, we're just looking at A and D, just these two. So again, we have two sides of our parallelogram already. So the rule is opposite lines are equal in length and parallel. Opposite lines are equal in length and parallel. So I can complete the parallelogram with the two existing vectors. And if I go to the corner of that parallelogram and draw a line straight back to the origin, force or vector E now shows me the combination of A and D. And if I knew the proportionality constant, I could measure the length of that vector and tell you exactly the strength of the force and the direction. Now, because B and C are accounted for in D, and I take A and D, and I come up with their combination being E. E is the combination of all three. So if all three forces A, B, and C were acting on some object right here, the combination of all three would be vector E. And so that's how we would apply the parallelogram to multiple forces acting on an object when the forces are unbalanced. So let's just say that, what object could we use? I always use a soccer ball just because it's easier. If you can imagine a soccer ball sitting right here, and somebody comes in this direction and kicks the ball here, going in this direction with that much force, and somebody comes from this angle and kicks the ball right here with this much force, and somebody comes from this angle and kicks the ball with that much force. If they don't run into each other and hurt themselves, and they all can accomplish kicking the ball at the same time with that much force in those three directions, the ball would go there. That's what would happen to it. So that might be another way to kind of think about it from a real life perspective. So that's 15.4. It really just talks about how to apply the parallelogram method to unbalanced forces when there are more than two. So we just take the parallelogram method and do it twice, basically. So that's 15.4. Pretty straightforward. 15.5, however, not so straightforward. So let's work through this a little bit. 15.5. It says, in the preceding sections, you saw that forces are vectors and that vectors can be added using the parallelogram method. If you guys watched my video earlier, I don't like the word added. I like to say combined. So I'm going to write that in my book because it's my book and I can. Added just makes you think about adding numbers, like 2 plus 2 is 4, and we can't add vectors that way when they're going in different directions in a plane. We can combine them using a parallelogram method. So all of the forces acting on an object can be combined, silly book, to find the net force on an object. For example, in 15.9, which we're looking at right here, forces 1 and 2 combine, not add, to form this net force right here. Now, what we're going to do in this section is look at this backwards, in reverse. So looking at this in reverse, we can think of any single force as being the result of the addition of two forces. So now what we're doing is looking just at this. We're going to say, okay, if we have one line, and this is the net force, where did that net force come from? So we can go work backwards and figure out what the components are. So component basically is what two forces combine to create net force. Okay, so we can work backwards to figure out the net force. So they're outside. I put them outside. Yeah, that's it. Thank you. He probably thinks I'm sitting here talking to myself. Thinks I'm crazy because I'm sitting in my room recording this by myself. Okay. Yes, I'm sure he thinks I'm crazy. Okay, so here we go. So what we can do is we can look at a single force and work backwards to figure out what two forces combined to form that net force. So basically what we could say is that forces 1 and 2 are the components of the net force. Okay, so components, so even if we go back over here, we can say that these are the two component forces, and if you do your parallelogram, you can figure out what the net force would be, something in that direction probably. So these are the two components to create a net force. These are two components, and these are two components. Okay, so what we're going to do here is try to work backwards. So it says, it is often useful to think of a single force as being made up of two perpendicular components. This is the key to this section right here, perpendicular. I'm not sure why, but it does not explicitly come out and tell you that we will absolutely be looking at perpendicular components, but just by suggesting it here, that's what they want you to do, is to look at perpendicular components. So then it goes on to tell you how you can do that. So I'm going to give you my version. Let's look at, let me find a blank sheet of paper over here. Okay, so if I have any net force, it doesn't even matter what it is. Let's draw a line this way, just for fun. And we're going to draw it like that. Okay, so let's say that's my net force. Oops, can you see that? There we go. And I want to figure out what two forces were combined to create this net force. So I'm going to call this NF for net force. Okay, so now here's the thing, and this came up when I was teaching my kids this. There's probably a bunch of different vectors that could combine to create this one net force. So instead of thinking of all of the different ways we could draw vectors to create this net force, we're just going to stick with components that are perpendicular to each other, because that makes your life a heck of a lot easier. So here's how I'm going to start doing this. So if this is my net force, I'm going to start at the origin, and I'm going to draw perpendicular lines. So actually, the easiest way to do that is straight up, vertical, and then horizontal. So I'm going to, from the origin, I'm going to go like this. I'm just going to draw a really long line, because at this point I don't know how long that component needs to be. So I'm just going to make it really long for now and show you how we're going to accommodate that in a minute. And then I'll draw a horizontal component. Okay, so now I've got a net force, and I've got these two components that are perpendicular to each other. Now, if this is the net force, if you recall, when we had the two components, we drew a parallelogram, and then the corner of the parallelogram gave us the net force. So now I can do my parallelogram backwards. I can say, okay, if this is the corner of the parallelogram, and I know that these are two of the four sides, I'm going to draw a line parallel to this one, starting at this corner and going back in this direction. So let me make sure I do that well. So I'm just using the net force and doing the parallelogram backwards. Okay. So again, parallel to each other, opposite, parallel, and equal in length. And the same thing on this side. I'm going to go to my corner, and I'm going to draw a line parallel to it. So let's move it this way a little bit. Okay. Hopefully that's parallel. I'm not the best. It's pretty close to being parallel. Okay, so I started with my net force, and I drew two components that were perpendicular to each other. And now to figure out how long those two components should be, I use the parallelogram method. So now I know this component here is only going to be this long. It's going to end right here, because the parallelogram tells me that. This component is going to end right here, because the parallelogram tells me so. So to create this net force, we can have this vector and this vector that combine to create that. So what I just showed you is how to work backwards. So we start with net force, we draw a vertical and a horizontal component. Then to figure out how long those components should be, we start with the corner of the parallelogram and do it backwards. So this is the corner, I'm going to draw a line parallel and opposite, equal in length, draw my second line parallel, opposite, equal in length, and then that parallelogram tells me how long those two components should be. So let's measure them and see. Let's make up a proportionality constant so we can figure this out. Let's see, this is we're going to do 1 Newton per centimeter. Oh, that's 5 centimeters. That works out very well. That's a 5 centimeter line. So my net force is 5 newtons, and my proportionality constant is 1 Newton per centimeter. Okay? Or I could say 1 centimeter per Newton. It's the same thing. In this case, it's the same thing. So if I want to figure out exactly the strength of these two components, now I can measure them. I can say this component is almost 5. It looks like 4.9. This one is 4.9 newtons in this direction. And this little tiny guy over here is 1.2 newtons. So I start with a 5 Newton net force, I work backwards, and I come up with a 1.2 Newton force going in this direction, combined with a 4.9 Newton force going in that direction. to create the net force. So that is how we work backwards using the parallelogram method. And again, these two are called components. Components. So the two components combine to form the net force. And so that's how we figure that out working backwards. Okay, and then they give you a question over here, not a question so much as a scenario, about pulling a delivery truck or pulling a cart onto a delivery truck using a ramp, and they give you the weight of the object and then the force the force of gravity pulling the cart this way, and then what its third component force would be, or the second component force would be if you look at weight. So you can kind of read through that. That should basically support what I just talked to you guys about in terms of how we figure out components. So that's 15.5, is really taking a net force, working backwards to figure out what the two components are that make up the net force. Again, keep in mind, at any point, see if you look at this one, for example, these two components are not perpendicular to each other. So it's not only perpendicular forces that can combine to create a net force, but just to give you some practice and to start from an easy place, that's why we consider perpendicular, because it's just easier. We have the net force, let's draw a vertical and a horizontal component, make them perpendicular, and kind of work from that angle. Otherwise, we could probably come up with, 10 different sets of component forces that would all combine to form this particular net force. So keep in mind that there are probably lots of different components you can come up with, but in this instance, in the way that the book is presenting it, starting at this point, we're going to look at just the perpendicular components. And I hope that helps get through 15.5. If you've got any questions, please feel free to ask me or Mrs. Kurt.